right. So, let's get started with the rest of our immune system. Alright. Okie dokie. So, last time we started looking at the third line of defense. And the big thing was, mostly what I did was to go through and introduce to you guys, again, the macrophage is an antigen presenting cell, how a macrophage can communicate with the lymphocytes. Where are you? Okay, so a macrophage becomes an antigen presenting cell, engulfs a pathogen, presents the antigen of it and on its MHC2, which I'm going to draw it here because I'm going to use it for helper T cell activation. All right, so we have a macrophage. So I'm going to draw it like a dendritic cell, make it pretty. Okay, macrophage has on its surface your MHC1s. The MHC1s have the autoantigens, right? So that's MHC1. We will have those all over the place. And when it takes a pathogen, it takes it inside, it will engulf it and present its antigen on its MHC2. So this is the MHC2. And let's show it like this. This is pathogens antigen, all right? And this is a macrophage that has become an APC now, okay? Then I talked about the lymphocytes, B cells, T cells. So we have, these are the three that are responsible for your adaptive immune response or specific immune response. We said it's specific because it targets an antigen, it's an antigen specific. It is adaptive, it decides whether it needs to activate both B cells and cytotoxic T cells or just B cells. It has a memory. Every time they get activated, they will produce a group of memories and a group of active ones. So therefore, from now on, you will have immunity. Then we talked about what was B cells, what was T cells, and I'm going to go to the one that shows both receptors and talk about them. So T cells, we said they have a T cell receptor or TCR. That is, will have one antigen binding site. Each T cell has a specific antigen binding site that recognizes only one antigen. To differentiate between helper T cell and cytotoxic T cell, helper T cells only respond to antigens on MHC2. Therefore, they have CD4 that confirms that it's MHC2. Cytotoxic T cells will only respond to MHC1s. Other way of looking at it, helper T cells respond to antigen-presenting cells. Cytotoxic T cells will only respond to virally infected cells. Helper T cell responds to exogenous antigens on MHC1. Cytotoxic T cell responds to endogenous. Remember, that's when you have a foreign antigen on the surface of your cells. Helper B cells have their B cell receptor has two antigen binding sites. They don't need any CD4 or CD8 because they will just respond to an antigen that is roaming in your fluids. And then last thing we looked at was clonal deletion, that each of these receptors are going to be exposed to your own antigens, and if they recognize any self-antigens or any self-markers, they are going to be deleted, completely destroyed, and never made. Okay, so now let's look at immune response and how it goes through this process. First one we're going to look at is activation of helper T cells. So again, helper T cells' job is to basically coordinate your adaptive immune response. They are the one that communicate with the macrophages, the antigen-presenting cells, and based on the information they get, they will then decide whether it's going to be a B cell only response or B cell and cytotoxic T cell response. Okay. So when a macrophage actually becomes an antigen presenting cell, it starts releasing a chemical called interleukin 1. Okay. So it starts releasing interleukin 1s into the media, and interleukin 1, which we shorthand, we refer to it as IL. Interleukin 1. This is a cytokine here. Interleukin 1. IL-1 attracts all of the helper T cells. So if this is the first time that this macrophage has been exposed to that pathogen, this is the original time, the only time, first time that this body has seen that specific pathogen, this is the first time that its helper T cell is going to become active. So the helper T cells all come, and what they do is they're going to find the MHC2, try their TCR, and see whether or not their antigen binding site of their TCR recognizes the antigen, and their CD4 is going to double check that that antigen is on MHC2. So here, I'm going to draw one that it won't respond. So helper comes here, and let's say that its TCR looks like that. And this is its CD4. So this helper T cell is going to go there, try to attach to this with the TCR. It's not matched, so it won't even try anything. This one will move away, nothing will happen to it. But the helper T cell that has the matching antigen binding site, so the TCR comes and matches the antigen that is being presented. So it's a match. That's the first, what I call handshake. Second handshake, as soon as that happens, CD4 has to connect to MHC2 and confirm that that antigen is being presented on MHC2. That's the second handshake. When these two happen, now our helper T cell becomes fully active. And it starts releasing cytokines that will attract B cells and cytotoxic T cells to it. When it becomes active, it will separate and divide into memory cells that look identical to it. So that single cell now starts producing clones of itself. So where you had only one helper T cell that looked like that one, when it's fully activated, it goes separate and then starts dividing and creates many copies. A group of them are memory cells of helper T cells looking like this. They're going to be taken to your lymph nodes and stored. And the other ones are called effectors or active ones. Effector T cells, helper T cells. These are the ones that are active and now are going to go work on B cells and cytotoxic T cells. All right? Simple. That's how a helper T cell becomes active. They are all attracted to macrophages. When they go, they immediately try to find the MHC2, they will check their TCR, T cell receptor, to see whether it's a match for that antigen. Then if that is so, the CD4 confirms that it's MHC2. This helper T cell is now fully active, will divide, release chemicals such as interleukin-2 and all of that to bring other things to bring B cells and cytotoxic T cells. And from that point on, based on the information, remember we have 2 helper T cells, and I don't want you guys to worry about that. Just for this class, we're going to keep it as simple as saying, based on what you see there, the helper T cell is going to either choose to activate just the B cell or both B cells and cytotoxic T cells. Let me show you the animation. This one at the end of it is talking about super toxins too, and I will stop it. I don't want you guys to know about super toxins right now. This is actually what toxic shock syndrome does. Have you heard of it? Women, most guys don't know because of tampons.
Antigens are normally processed by antigen-presenting cells and presented to T helper cells on class II MHCs.
So this is a macrophage. It is presenting what this video is missing, is showing MHC1. So it would have both of them, but to simplify it, they're just showing MHC2. So it has taken the pathogen inside, processed, and it's presenting the antigen on it. Now they're going to show different helper T cells being attracted to it and trying to figure out if they're the ones that should be chosen.
Only the T helper cells with T cell receptors capable of interacting with the antigen are stimulated to produce cytokines. The activated T helper cell stimulates only B cells that react with the same antigen, thereby limiting the response to the production of antibodies that were presented. Superantigens, such as the toxic shock syndrome toxin.
All right, we're going to stop it there. They did talk about cytotoxic T cells, but helper T cells will have an effect on cytotoxic T cells too. They just showed B cells there. All right, everyone good? Keep it that simple. All right. Now, let's see what happens if, so that was helper T cell. Let's now look at cytotoxic T cells. So what happens to cytotoxic T cells? Cytotoxic T cells, remember, they will be responding to inflammation too. All your white blood cells, as soon as you have inflammation in an area, they're traveling there already to begin with. So your cytotoxic T cells are there too, and they are constantly checking your tissues in the area of inflammation. So let's say, remember the twin cytotoxic T cell for this guy is also, we have one of them. So they're coming to the environment, to that area where you have inflammation. So here, what I'm drawing is an infected cell. So virally infected cell. Remember, in a virally infected cells, in all of your cells, so in this case, the virus has gotten inside. All of our cells are programmed as soon as antigens are made inside of us. Don't question it. Those brand new antigens, when they're made inside, you take it and you present it to the surface on MHC1. So because it looks like that, it's going to take the antigen that it was made inside and presented on MHC1s. So this is my MHC1. So it will send it to the surface and start putting it on MHC1s on the surface. Viral antigen. Now, cytotoxic T cells come and keep checking. So again, we have a variety of different kind of cytotoxic T cells. The only cytotoxic T cell is going to respond to the cell that has the matching TCR. So for this case, this is its TCR. So it matches the MHC1, a foreign antigen that is presented on MHC1. As soon as that happens, remember it has the other receptor there called CD8. CD8 has to confirm that this is MHC1. If it is an antigen that is on MHC2 and it's matching to it, it will shut down. So cytotoxic T cell first on its own comes to the area. We'll keep searching your tissues, and the cytotoxic T cell that has a TCR with the antigen binding site that matches the antigen, that's its first buzz. The second buzz is the CD8 has to confirm that it's MHC2. This makes this cytotoxic T cell partially active. This partial activation is basically this, and I don't know how to draw it, and unfortunately the animation doesn't show it. The partial activation is basically now there are receptors suddenly on the surface of the cytotoxic T cell. There are receptors that are produced and sent to the surface, and these receptors respond. So now it suddenly produces receptors and sends it to the surface. These receptors respond to cytokines released by helper T cell. Up to that point, this cytotoxic T cell, if it doesn't match it, it can be smack dab in the middle of these chemicals and it wouldn't even know. The partial activation or the first step activation of it, because it recognized a foreign antigen on the surface of a cell with MHC1, that allows this cytotoxic T cell to produce these receptors on the surface, which we didn't have before, that now would respond to cytokines released by helper T cells. Example of cytokines are IL or interleukin-2, tuber necrosis factor, TMF, and some other ones. So tumor necrosis factor, we call that TNF, tumor necrosis factor. Now, the helper T cell has produced them, and this cytotoxic T cell here goes fully active. Stays attached to the cell, releases now enzymes and proteins that do two things. Force this cell to go through apoptosis. So that was the programmed cell death. So it's going to shut everything down and try and kill itself. And there are also other proteins that it will force, cause production of holes in the surface of this cell. So lysine. This is how a cytotoxic T cell kills the virally infected cell. Once it's sure this is fully taken care of, Then as soon as it separates, before finding any other cell, it does again the same thing. It will divide and make memory cells and then active cells or effector cells. Memory cells don't do anything, they just go to your lymph. Active cells are now fully active and they will just search, and any virally infected cells they find, they will immediately attach, and they don't even need to wait for the helper T cell because they already have the receptors. Everything is from this one, they are fully active and they're going to kill other virally infected cells. The animation that I have does not talk about the helper T cell helping it, but it is important to know. If you don't have the proper helper T cell, so remember we had type 1, type 2. If type 2 responds to cytotoxic T cell. If none of the type 2 helper T cells get activated and produce the right chemicals, this thing can produce the receptors. But because it's not releasing, getting the cytokines, and its helper T cell did not get active, it will not get fully activated. It will shut down. So if it's a bacterial infection and really there's nothing there, its helper T cell will not release interleukin-2 and tumor necrosis factor and all of that. They're like, we don't need cytotoxic T cells. All right, let me show you the animation. And again, the animation doesn't talk about helper T cells. Khan Academy has a good one, and I think Amoeba Sisters in theirs, they talk about also that helper T cell needs to give it a go-ahead.
When a virus infects a cell and synthesizes viral proteins, some of these proteins are and are displayed on the surface of the infected cell. Cytotoxic T cells interact with the virus-infected cells by recognizing both the viral antigen and the class I MHC. The cytotoxic T cell is infecting a virus. When a virus infects a cell and synthesizes viral proteins, some of these proteins are degraded to peptide fragments. These peptide fragments form a complex with class I MHCs and are displayed on the surface of the infected cell. Cytotoxic T cells interact with the virus-infected cells by recognizing both the viral antigen and the class I MHC. The cytotoxic T cell then releases perforin molecules which create pores in the plasma membrane. Enzymes called granzymes are delivered into the pore, which cause the cell to undergo apoptosis. Cytotoxic T cells only bind to foreign proteins presented on the surface via the class I MHCs. Self-proteins are not recognized. Once the cytotoxic T cells have released their perforins and granzymes, they detach from the infected cell and move on to other target cells.
So two things they did mention, the helper T cell and how the fact that this cytotoxic T cell now is going to divide and produce clones of itself. Some of them are going to be memory and some of them are going to be the active ones that are going to kill others. Okay, now B cells. Let's look at B cells. So I'm going to draw B cells here. B cell. B cells are also attracted to the site of inflammation. B cells would only respond to exogenous antigens. So meaning these are antigens that are found in the environment. So pathogens that are roaming around outside of your cells in the fluids. Interstitial fluid, lymph, blood. Okay. So we use the example of this virus. Let's use the same virus. So B cells on their own are coming. And you have the B cell, they have receptors on their surface, and they have different antigen binding sites. About 99% of the time, this is how B cells get activated. They also have a two-step activation. Partial activation when they recognize an antigen on their own, and then they need a final say-so from the helper T cell, which is this, in this case, is extremely direct. Let's make that. These are the BCRs. And this is our twin helper T cell, so BCR or B cell receptor with the antigen binding site. This one in the environment, let's say, it comes in contact with the virus. And its TCR, and its BCR recognizes the antigen. So let's say even one other one goes here and recognizes and attaches to another virus there. When this happens, the BCR is taken inside by the B cell. So it goes through phagocytosis, so two antigen binding sites recognize an antigen. So they attach to this virus. B cell then does this. It takes it inside, engulfs, takes those receptors inside, takes the pathogen, and with the pathogen then processes the pathogen, takes the antigen of it, and attaches it to MHC2 and sends it inside. Takes the antigens, takes MHC2s, combines them together, and puts it on the surface. So now it sends MHC2s to its surface with the antigen that it recognized. Releases a certain cytokines that attracts helper T cells again to it. So this is first step of activation. A B cell goes to the site of inflammation. If its BCR, B cell receptor, recognizes an antigen on a foreign cell, it will take that foreign cell or pathogen, in this case we have a virus, it takes that virus with its antigen inside attached to its B cell receptor, removes the antigen that it recognized and attaches that to MHC2, takes it to the surface. Now this becomes a presenting B cell. What it likes to present again, its helper T cell. So it awaits to see, did my twin helper T cell become active? Active helper T cells come and check presenting B cells. The one that recognized this one with its TCR now this is active helper T cell. Comes and attaches to it. It's CD4, confirms that that's on the MHC2 of this B cell. And then helper T cell, when it does this, it basically releases interleukins for interleukin 4, 5, 6, and some other cytokines, releases them, and that makes this B cell to become fully activated. So release cytokines such as IL-4, 5, 6, some other ones, and it makes this B cell fully activated. The B cell then separates from its active helper T cell, goes and takes in all of its receptors, gorges up, gets bigger, and divides into memory B cells that go away, and they will look the same with the same receptors. Or the active cells for B cells are called plasma cells. Plasma cells won't have any receptors. They're filled with endoplasmic reticulum and all of that, and their job is to release antibodies. These guys will make antibodies and release them to the outside. So, antibodies or immunoglobulin. That means protein, immune proteins, same thing. Antibodies and immunoglobulins, they're the same. Shorthand for antibody is AB, shorthand for immunoglobulin is IG. Anytime you buy antibodies and all of that, that's what you see. In blood tests, you see IG, IgG, IgA, IgE. All right, that's how they report it. Then antibodies, we'll talk about it, how they go and they have a specific function in attacking. So, B cells, normally, 99% of the time, they will go to the site of inflammation. At the site of inflammation, they check your fluids in the lymph, in the blood, in the interstitial fluid. They look for pathogens. If their receptor, B cell receptor, BCR, the antigen binding site recognizes an antigen, it will attach to that pathogen. Then it will take that receptor attached to the pathogen, the whole thing, it will engulf it, like phagocytosis of its own receptor attached to a pathogen. Takes that pathogen, removes its antigen, and now shows it on its MHC2. So sends that to the surface and says, hey, helper T cell, am I the one? It wants to make sure that it just didn't find one, and this is not the one that is causing the trouble. Maybe it was one pathogen, it just found it by mistake. The actual pathogen that it needs to, that we need to attack is something totally different, and this is not the B cell. So it will present and wait for a helper T cell. Active helper T cell will find it. They keep checking the MHC2s of the B cells. If it's the right one, its helper T cell is already there. It will attach, confirm with CD4 and everything, and release cytokines. The B cell will take all those cytokines, then it decides I am fully active. When it becomes fully active, will take in all of its receptors in and gorges up, and then suddenly goes crazy, differentiates into memory cells. Memory cells look like itself. It will produce thousands of that. But they won't be activated, they're not presenting, they will go and they won't do anything. Plasma cells are the active one. These won't have any receptors on their surface. They're just protein-making machines. And the protein that they're making is the antibodies or immunoglobulins, and they release them. We'll look at that, what they do in a bit. Okay, so everyone good with that? I have to give you an exception for B cells. Very rare cases. A B cell can go fully rogue and get fully activated without the helper T cells go ahead. And in that case, the only time it can do this is when 99% or 90% of its receptors have made contact with the same antigen. What does that tell you about the steps of infection? If when it gets inflammation, beginning of inflammation, it goes to the site, and rather than 1 or 2 antigen binding sites attaching, pretty much all of them get attached, maybe except for 1 or 2. What does that tell you about that infection? Think of it. Is this infection at the beginning step? No. Right away, we have a ton of this pathogen there, or this pathogen is huge. The B cell, and in this case, your body basically says, I would rather be wrong and start attacking this thing than wait for that single memory cell, helper T cell to find its way to antigen presenting cell, then become active, then come and confirm that it's me and then fully activating. In that case, the B cell immediately pulls everything in and goes and produces plasma cells because it's worried that this is way too late. I need to start producing antibodies. Something's wrong. In many cases, immunity, this is what happens. Suddenly you have a lot of them there, and these memory B cells are like, I'm going to get fully activated, release antibodies.
Would that be like something like a sepsis or something like that?
Sepsis, it could be that you were injected like by a large dose of a pathogen, like you stab yourself with a needle full of a bacteria.
Because sepsis just takes over.
Yes,
and
all over.
Things shut down.
Exactly. So your
freaks out.
body doesn't have, and hopefully in those cases it will happen. Or this is something huge and your body needs to start attacking. All right, so the B cell one is pretty long and it's okay. It's not bad. By the way, they call this clonal selection. When B cell activates, they call it clonal selection. The same term works for everything, meaning this single B cell is now selected and can produce clones of itself. Same opposite of clonal deletion.
The immune system can produce antibodies against millions of different antigens. B cells are constantly produced from lymphoid stem cells and are found in the blood and lymphoid tissues. Each B cell can synthesize only one of the millions of possible antibodies and display this antibody on its surface. When an antigen meets a B cell that has a surface antibody of the proper specificity, it binds to the antibody, stimulating that B cell. B cells that do not have the correct surface antibody are not stimulated and do not develop further. The stimulation of only the B cells that carry antibodies that react with a particular antigen is referred to as clonal selection. The activated B cell swells and begins to divide rapidly, producing a B cell clone. The B cells then differentiate into plasma cells and memory cells. Plasma cells produce large amounts of the antibody specifically targeted to the antigen that initiated the response. Memory cells remain in circulation but do not produce antibodies. These memory cells can become activated later when challenged by the same antigen, allowing for a rapid and intense secondary response. It is important to note that many antibody responses carried out by B cells require signals from T helper cells. The T helper cell is stimulated by an interaction with an antigen-presenting cell, such as a macrophage. The macrophage ingests the antigen, digests it, and presents fragments of it on its membrane via a class II major histocompatibility complex, or MHC, molecule. The macrophage then activates a helper T cell that carries a T cell receptor capable of recognizing the antigen fragment presented on the class II MHC of the macrophage. The B cell presents fragments of the same antigen on its surface using class II MHC molecules. The activated T helper cell interacts with the B cell and secretes chemical signals called interleukins to stimulate the B cell to differentiate into a plasma cell and produce antibodies.
All right. So, everyone okay with activation? Now, antibodies. We have different classes of antibodies. So when a B cell gets activated, the plasma cell typically at first starts producing the top one, what we call IgM. So immunoglobulin M. Think of it as M as mega. What this is they actually take, which an antibody is similar, identical to the B cell receptor. So IgM takes 5 of those receptors, attaches them together at the constant region, and creates this huge immunoglobulin. This immunoglobulin has 10 antigen binding sites. So that means it can bind to 10 antigens really fast. Plasma cells typically first produce a lot of IgM to start removing them from the environment as fast as they can. Then they switch to IgG. IgG is just like a simple receptor with 2 antigen binding sites. Why? Because IgG is small and can get in between the tissues and get anything that has gotten into interstitial fluid and get there. These are the main ones that I want you guys to focus on. IgG actually is so good it can even cross placenta and get to the fetus if it needs to. IgA is a dimer. It's 2 of them attached together. They are typically released in saliva, tears, breast milk. Okay. IgE, it's very similar to IgG, but for whatever reason, they go and attach to the surface of mast cells. And this can result typically in allergic responses. So if you by chance produce IgE for pollen, and it attaches to the mast cells that you have in your nasal cavity, every time you smell that pollen or it goes up into your nose, that IgE on the mast cell goes crazy and mast cell produces histamines and you have your allergic, congestions and all of that. Okay. IgD is actually the name for the B cell receptors. They call them IgD. So if it's attached to a B cell, they call it IgD. For you guys, what I want you to know mostly and pay attention to is IgM and IgE. The IgG. IgM and IgG. Those are the 2 main ones that keep fighting. Now, what do they do? This is the list in writing. I'm going to use the image. They can be good at the process of neutralization of the pathogen. So they can attach to the pathogens, for example, for the virus, they can attach, if it's against the glycoproteins or the spikes, they attach to it and that virus no longer can attach to its host. Like putting a cat, putting their blindfold for them. They will be right next to their host cell, but they can't go inside because they can't have the interaction of the glycoprotein and the host surface cell. Like having the key, if you put the key in the cement, you can't insert that key and get inside, all right? So that's immunoglobulins. They can neutralize bacteria even by interacting with the other proteins in the surface. So They do something else we call agglutination. Agglutination is basically when they clump them up together. IgM is fantastic at that. But IgGs can do that too, because that constant region can actually make connection with the other ones. So they can agglutinate, stick them together, and that pathogen won't work. They can neutralize, for example, toxins. Many times toxins are very small proteins or soluble proteins that your macrophages can't attack and remove. But if you produce antibodies, the antibody was attached to the toxin, and then that toxin will precipitate. The antibody-antigen complex is no longer a soluble protein. It's insoluble, it precipitates, and your macrophages see them and remove the toxin. And finally, in all of these cases, not finally, one to last. In all of these cases, the constant region of the antibodies is seen as an opsonate. So all your macrophages have receptors on their surface for the constant regions of the antibodies. So when the antibody is attached to this guy, a macrophage can go easily just grab that antibody and pull it in. So it enhances phagocytosis. It always helps phagocytosis. They're not going to poke holes. They're not going to do anything like that. They cannot kill the bacteria or the virus. They just can inactivate them. And the final thing is antibodies are triggers for complement cascade, the classical pathway. Let me show you the animation for that, and then I'm going to create a chart comparing alternate pathway and classical pathway that will help you a lot. Alright. So this one will show first the classical pathway, and then it will show you the alternate pathway, and it could show you. So what's difference between these two? In classical, you actually have the activation is different, what proteins get respond to it. So let's say alternate and classical. So activation, let's go over alternate one time. So it's C3. For alternate, remember it was C3 that splits on its own, some of it. If they attach to a pathogen, they become active. Once they are active, the whole thing goes and they produce a C3 convertase. The C3 convertase in them is C3b-BB. C3 convertase later on makes C5 convertase. C5 convertase was C3b, BB, 3b. And ultimately that produces MAC. All right, the response is MAC. C3a makes inflammation go up higher. I just wrote INFL for inflammation. C5a brings more neutrophils. And C3b is opsonate. For classical pathway, the activation is actually dependent on C1 finding an antibody. So a C1 antibody complex has to form. Then that's going to eventually make a C3 convertase and C5 convertase. C3 convertase for them is for the classical pathway, the C3 convertase is made up of C4b, 2b. C5 convertase is C4b, 2b, 3b. The outcome is exactly the same. So let me show you the animation. The animation obviously is way better at showing this thing to you guys. By the way, the animation, look at C1. How you have C1Q, C1R, C1S. There's 3 different portions to C1 protein. I do not care for you guys to know that. What is the function of each of them? Just know that C1, if it sees an antibody, it will attach to the antibody and start activating the classical pathway.
The complement system consists of a group of over 30 serum proteins that play an important role in both innate and adaptive immunity. Complement proteins participate in host defense processes such as inflammation, attraction of phagocytes to an infected area, enhanced effectiveness of phagocytes, and lysis of cells. Complement proteins are activated by a cascading mechanism. There are 3 pathways of complement activation: the classical pathway, the alternative pathway, and the lectin pathway. The classical and alternative pathways are demonstrated in this animation. The classical pathway requires interaction of antibodies with an antigen, usually on a cell surface. Following binding of antibodies to cell surface antigens, C1, which is composed of 3 proteins, R, Q, and S, attaches to the constant region, Fc, of adjacent antibodies through its C1Q subunit. C1S then acts on C2, cleaving it into C2A and C2B. Then C1S cleaves C4 into C4A and C4B.
So, translation. Antibody attaches to the surface of the pathogen. Remember, complement only acts on cellular pathogens. Antibody attaches. C1 recognizes the constant region and will attach to it. Once C1 attaches to it, it's active. Now it's going to split a complement protein 2 and a complement protein 4. Splits both of them to A and B side. To be or not to be. B is the one. So complement protein 4B and complement protein 2B will connect at the surface and will create the C3 convertase. So don't worry about S does this, R does that. Just complement C1, an antibody complex, now is going to split C4 and C2, allowing for C3 convertase to be formed.
C2b and C4b bind to the cell near the antigen-antibody complement complex, and C2a and C4a are released. This complex of C4b and C2b, called C3 convertase, has protease activity and cleaves C3 into C3a and C3b. C3b becomes bound to the cell surface, whereas C3a is released. C3b then absorbs to C4b2b to form C4b2b3b. This structure is called C5 convertase. The alternative pathway does not require the presence of antibodies. Activation begins with cleavage of C3 into C3a and C3b, either spontaneously or by a blood protein. C3b binds to foreign substances. Factor B, a blood protein, attaches to C3b and is cleaved into 2 fragments, BA and BB, by factor D, forming C3bBB, analogous to C4b2b. Both structures, C4b2b and C3bBB, are called C3 convertase. C3 convertase rapidly cleaves more C3 into C3a and C3b. C3 convertase is further stabilized by propertine, which allows another addition of C3b, forming C5 convertase.
I seriously think this should be used by highway patrolmen to figure out if a person is drunk or not. All right. I'm not going to show the other animation because it is the function of it. So looking up here, again, if you really seriously understand this or have a basic understanding of this table and the chemical formula for the C3 convertase in each of them, C5 convertase in each of them, then you can actually even work your way through trying to explain what is happening, even if I ask you completely tell me what happens in the classical pathway, which I typically don't, because you guys get into that weird area. Under normal condition, you will explain it to me, but on an exam, you just go crazy. But something like this is very important. Alternate pathway. How does alternate pathway get activated in complement cascade or get started? C3 splits, and if any C3b, find a host and attach to, not a host, sorry, find a pathogen and attach to it, that C3b is now active, it's going to eventually lead into C3 convertase formation, which in alternate pathway is C3b-BB. That leads to formation of C5 convertase, C3b, BB, 3b. Once C5 convertase is there, it's going to split C5s. If you have a C5b on the surface of the pathogen, it's going to call a 6 to it, a 7, an 8, and multiple 9s make MAC. In the process, C3a raises inflammation. C5a brings neutrophils to the site. C3b anytime is an opsonin too, and all macrophages can get to it. Classical, you have to have antibodies, immunoglobulins release. C1 attaches to the constant regent of the classical, of the immunoglobulins, then it's fully active, splits C4 and C2. The part B's of these come together, make C3 convertase. They break down C3s. Part B of C3b comes and attaches. It makes C5 convertase. After that, everything's the same. Okay? And in this image, it's kind of showing that too. So you have antibodies. C1 gets active. Then it's going to split C2s, C4s, and C4b and C. Oh, this is wrong. It's showing C2a coming. So it's everything is B. So C2b, C4b come together and make C5 convertase. All right, and that's the MAC. Okay, I know. Try to learn this, and then from that, try to look at the animation and explain the process to yourself. Mute it so you don't listen to them. All right. So when you have your full set of adaptive immune response getting activated, helper T cells then, in conclusion, their job is to activate cytotoxic and B cells. Cytotoxic T cells will attack any cell that is virally infected and kill them. The way that they get activated, they have to find the infected cells. That partially activates them. Now they are capable of receiving cytokines from an active helper T cell. If the active helper T cell is activated and is releasing those cytokines, cytotoxic T cell is fully activated, kills, and makes memory and active cytotoxic T cells. B cells go to the site of inflammation on their own. They try to find anything that is not supposed to be there. If they attach to something, they'll take the receptor in, take that antigen, present on MHC2. Then they're going to wait for the helper T cell that is active to come and attach to them. If that happens, then that releases cytokines to make B cell fully active. They make memory cells, plasma cells, antibodies are released. Rare conditions, they can get activated fully on their own. That's if majority of their receptors bind to an antigen. Antibodies, we saw processes, neutralization, agglutination, precipitation, and then they can be opsonins. They can cause activation of classical complement pathway. Last thing I want to say with regards to the memory and immunity and how you can have immunity. First time, and we're just going to look at B cells here. First time you're ever exposed to a pathogen, we refer to it as the primary infection and primary response. It will take a while. So incubation happens, then the number increases. We call that infection. Then infection leads to illness, full-blown signs and symptoms, and all of that. Typically, there is a latent period that your lymphocytes are not active. The reason for that, again, is because you have only one of each of these cells. And by the time they are exposed, the helper T cell is exposed to the macrophage, and it says, okay, you're the actual one. So cytotoxic T cells and B cell might have found the right cells and the right pathogens and all of that. But it takes a while for activation of the helper T cell, because there's one helper T cell that now has to find this macrophage. But once that helper T cell is activated, it can go and activate the cytotoxic T cells and the B cells. So it takes a while, and that's why the patient has signs and symptoms. Primary response, the plasma cells first produce IgMs, then they start producing less of those and start increasing the IgG. They will have an overall response, and then after a while, that response goes down and they stop producing immunoglobulins. Second time you're exposed, you have a ton of memory helper T cells, you have a ton of memory cytotoxic T cells, B cells. So that helper T cell becomes fully activated, and this is the time the patient doesn't even show signs and symptoms. They might even just say, something's not right, but then they bounce back. This time, when a memory B cell becomes active, it knows that it was a memory B cell, and it's not the naive or the first one. This one responds differently. Immediately, the plasma cells that are produced from a memory B cell massively produce IgM and IgGs at the same time, simultaneously, twice or triple the amount of time that they produce or concentration they produced the first time. And they keep them going for a very long, long time at high concentration, longer than what they did the first time. Because this is like, hey, you came back again? All right, let's deal with you the second time. Third time is going to be even more massive than this. And each time, again, you're producing more memory cells too. So now all of those memory B cells are going to get active. So this is why sometimes for some vaccinations, you see they go get a shot. A few months later, the child goes back, gets another shot. They go say it's a booster. Then a third one, and they're like, okay, she or he is should be vaccinated. All right?
So, you go ahead.
It's kind of like when you have an allergic response, your body doesn't really respond, but it's holding on.
Yeah.
It's like, I gave you a little reaction, don't do that again.
Yeah.
And so that's the memory B cells?
Yes. It's memory B cells, and then they get activated, so they produce antibodies
And
against
that's
them.
the high peak when
Yeah.
it's like, I told you.
Yeah, and
Right.
that's why you can get shock, anaphylactic shock, because now they start producing like crazy, and then it can actually go berserk.
So it's the memory B cells.
Memory B cells and the mast cells. Yeah.
I was just wondering, so let's say someone got strep throat for like the 30th time in their life, does that mean that by that time they should be able to fight it way better than their second or
Should
third?
be, but this is the key thing. Memory cells for each pathogen is different.
Okay.
Some you produce lifelong immunity. Some memory cells disappear, and some plasma cells get destroyed, and you lose the immunity against it. Like immediately for a while you can fight it, but then your body forgets. That's why people can keep getting strep throat.
Right, okay.
So your body forgets it.
Okay.
But typically, unless they show weird things, it shouldn't be as bad. But depends on the person's genetics. Like I said, some people don't ever produce immunity for chickenpox.
Right.
We don't know why. So it depends on the pathogen. That's why you have to, like flu shot. There's a different variety of the flu, but then also your body tends to forget about the flu.
Okay, thank you.
Jessica?
I was going to ask, like, this is the logic it's used to get rid of allergies in little kids.
Yes. So they start this time, what they do, in some cases, when you have allergies, like food allergies, this has been, works fantastic. They start giving you the allergen. This is something that your body should not have produced immune response to it. They start giving it to you at this very tiny amount. So it produces it. Very soon after that, they again give you that same little dosage. The little tiny dosage, they keep giving it to you, and you're like, your immune system is like, again, this thing is here. So in some of those cases, because it's not necessarily all B cells, sometimes it's just the mast cells. And the mast cells that have IgEs on top of it. So every time that mast cell gets activated, some of them burst. So what your body, they're trying to do is they're trying to tell your body, don't produce any IgEs for this. You're gonna see this every day. And slowly increase the amount. So finally you're like, the body is getting used to it and that they're no longer allergic to it. So, but you have to be, in some cases, you have to be very careful. As a child, I had severe allergies, like I would have hives all over to pollen and grass, and then one time, like my eyes, the white of my eyes got swollen so much that I was basically told not to move because it could burst. But I went to an allergic, like a clinic, and that's what they were doing. They tested me, they realized what I was allergic to, and then from that point on, at first it was like every other day I had to go and get shots, multiple shots where they had the allergens, like the whatever, in small doses. Then over time that got to 3 days a week, and then it got 2 days a week, then it got once a week, then it was like twice a month, and then now I just get sniffles, but I don't have that severe anymore. But the less you're exposed to it, like I am semi-allergic to cats, depends on the cat and the dander. I've always had cats. Then when I came here and I started college, it was like, okay, I can't take care of a cat. So I stopped having cats. My allergies to cats is now a little bit stronger than it used to be. Like in the past, I was like, no way, I'm allergic to a
So
cat.
if you were consistently
Exposed to it. In my case, I don't produce anaphylactic shock. So I have not so far, but some people suddenly their body goes to level crazy. All right, so that's how we get immunity. Immunity is because of the memory cells. All of them will produce memory cells. All right. Okay, types of immunity that we have. Immunity, first of all, is only when your adaptive immune response gets activated. Your lymphocytes, cytotoxic T cells, B cells, and helper T cells get activated. That's the only time you will show immunity. We have active immunity. Active immunity, as it's from its name, that means your body, your immune system became activated and produced a response. Active immunity can be brought on in a human being naturally or artificially. Natural is when you get sick, you got chicken pox, you survived, now you're immune to it. So you produce memory B cells, memory cytotoxic T cells, and you're good. Or in some cases, for tetanus. The person got tetanus. Tetanus is bacterial. They were very lucky. They produced some immunity and they survived. Now they become lifelong immune. So it doesn't have, in that case, only B cells get activated. Artificial is vaccines. So active immunity, artificial active immunity is vaccines. This time, they take the pathogen, they take its pathogenicity away, and they introduce the pathogen to you with the proper antigens. So however they make this into a weak pathogen or inactivated pathogen, they have to do it in a way that the antigen doesn't get touched. So it looks like the wild type, totally full-blown disease-causing pathogen. They give that to you, your body shows a response. You kind of will show a little bit of inflammation because it has to do inflammation. You feel a little bit, I'm not that great. The next day you're okay. Why? Because you don't get the disease. So that's, again, active. Memory cells. And in some cases it could be lifelong, it could be multiple years, like tetanus. Every 10 years you need a booster because they realize body forgets about tetanus. And you have to force it to, again, make memory, plasma cells, increase the antibody titer in your body. Passive, from its name, none of your lymphocytes get activated. So you're like, then how could I get immunity? Passive means none of your own lymphocytes got activated, but somehow you get immunoglobulins in your blood and in your fluids. Natural one, the only way to do that is a mother passing it to the child, to the fetus, or by breastfeeding, pass it to the infant. So they have immunoglobulins in their breast milk and the baby feeds, they will keep it, okay? The artificial one is the person shows immunity, they take their blood, they extract their immunoglobulins, and they inject the person with the immunoglobulins. Or they produce immunoglobulins by some ways that we're going to show you. Now they do. They can produce immunoglobulins, package it, sell it, and the person, when they're exposed to something, and typically you don't do this for every disease. You do this for something like the person is getting tetanus, they're exposed to tetanus, and tetanus can kill very fast. So you want to give them immunoglobulins until their body is ready to react, and their body will produce it. Meanwhile, like rabies, same thing. You want to destroy them because it will kill the person. Next, we're going to look at the artificial methods, immunizations. So, vaccines versus, which is an active artificial immunity, and the passive is anti-serum. And I'm not going to cover it now because we have Wednesday for immune system 2. This is perfect. Vaccines we can finish like within half an hour or so, and same thing with anti-serum. Then I'll be done and I can review for you guys. So if I have enough time to finish them really fast, but why? All right. Okay. So again, if you're starting to study, hopefully you started this weekend. If you're starting to study for these two chapters, 12 and 13, do it little at a time. Make sure you understand what is an antigen and all of that. Look at animations. Amoeba Sisters, very good animations. Khan Academy, K-H-A-N, very good animations. Animations here are good, semi-okay too. Draw it for yourself, go through it. A reminder for every chapter, remember we have that module at the end that has the activities that I was using when we were out for COVID. For these two chapters, again, there are questions there that kind of gets you into thinking. So they're like essay questions. Make sure you go review over those too. All right, so we'll review a little bit more. By the way, deadline for dropping any class is November 14th. W, I know your counselors say don't get W's, but W's are better than, I believe, a lower GPA if you're going into allied health. You can always explain a W as who goes and check and see, you know, the stories that you tell them. Honestly, half of these schools are getting all these letters that the person is doing this and has done that. None of them come and say, let me see your proof that you went and built like 10,000 homes in Alaska. But, so you can explain W and say, this happened to me, I couldn't continue. But not too many W's, all right? Okay, so November 14th. Okie dokie, guys. So, this